Lecture Joe here, and in this video we're going to take a look inside a cheap digital multimeter. So here we have the meter taken apart. This is the selector switch that we rotate to select different ranges and to switch the meter on and off. And you can see that on the back of the switch we've got a series of copper contacts, and they rest on these little pads on the circuit board and switch the meter between different ranges. The circuit board itself has the pads on this side and the LCD on this side, and then on the reverse we've got most of the components. So we'll take a look through and see what's what. Now, in order to figure out what's going on inside this meter, we've obtained the schematic diagram for the meter from the manufacturer, and here we've got a full schematic for this particular circuit board. So let's try to tie together some of these things. We've got a schematic here showing us the sockets that the probes go into. So this is where, on the real meter, this is where your red and black probes go for taking your measurements. And on the circuit board itself you can see the probes here, or the sockets here for the probes. On the schematic we've got 4 marked out. On this meter we've only got 3. That's because the small current range is combined on this meter. But it's more common to have this arrangement with 4. Where you do have the 4, you've got a common here which is always black, and your black lead stays in that permanently. And then you've got volts and ohms socket here, so you're moving your lead to there to take a voltage measurement or to measure resistance. And then you've got current socket here, amps, and a current socket here, the top one being for small currents, i.e. milliamps. So over here on the actual PCB, COM is at the bottom here, so that's where the black lead goes. Then we've got V in. It's probably hard to see it there on the writing on the board itself. You've got V in here, that's the second one up. So that's for voltage and current, voltage and resistance measurements. And then you've got a current socket here. You'll notice that on the current socket on the PCB, the first thing you see here is a fuse. And that's because internally, when you measure current, you don't expect the meter to add any additional resistance to your circuit. Therefore, the actual internal resistance of the meter when you're measuring a current is very low. The upshot of that is that if you mistakenly have your leads plugged into COM and current, as if you're going to measure a current, and you then put them in to measure a voltage, let's say on a 230 volt socket outlet, you've essentially put a short circuit across the socket outlet. So you've got to have some sort of fuse inside the meter that's going to blow there for safety. So you'll see a fuse there on the milliamp range. On this particular meter there is no fuse in the 20 amp range, which is bad. You don't want to use a meter out in industry that doesn't have fuses on both current ranges. Let's take a look, see where the fuse is. Here we are. So you see right beside one of the sockets here, we've got a trace going over to the fuse itself, and the fuse is marked at 250 milliamps. So that's on the current range that measures up to 200 milliamps. So the fuse is just above that. As I say, there's no fuse in this meter in the 10 amp range, which is a bit unusual, but that's just because it's a cheap meter. In industry, you got to make sure that all of your amp ranges are fused, and make sure you got the correct fuse in them at all times. There's no fuse, as you can see on the schematic here, there is no fuse associated with the voltage and ohms socket. And the reason for that is when you're measuring a voltage, the internal resistance of the meter is probably up in the region of 20 million ohms. So there's very little current flows along the leads and through the meter. There would be no point fusing that. I mean, you could never get any sort of fuse small enough to blow with that sort of current. You're talking microamps there. So when you're on the voltage and current ranges, it's a lot safer because there's no chance of your meter blowing apart in your hand. But when you're on the current ranges, that is a possibility if you're using a cheap meter here, and you've got your lead in the wrong socket. Or if you're using a good meter and someone has replaced the fuse with a bit of silver paper or some such thing. So always make sure that the meter's got the right fuse in it. Okay, so that was the first thing we've tied together here between schematic and actual PCB. The sockets themselves, where the probes go in, and the fuse. So let's see what else we can see. So you'll notice in the main PCB, in the main schematic, that we've got these strange little circular blobs, and they are really selector switches. So this can be connected to there or to there, this can be connected to there or to there, this can be connected to any of those 6, this can be connected to any of those, whatever it is, 8. Those selector switches, multi-way selector switches, are the selector switch on the front of the PCB itself. So whenever you rotate this and these copper wipers move over these pads, what's happening in the schematic is that a connection is being made between a common there and one of these other terminals. So it's really just a multi-way selector, and you can envisage that happening as you turn this selector around. The point of that selector is to select the different ranges. So we'll look at that in a moment. So this, all really, and probably those, all really tie to here. They're represented by this on the PCB. Now, why have all these selector switches? Well, you can see from the front of the meter that moving the selector switch around selects different ranges. So if we look perhaps at the voltage DC here, we can select between a 600 volt range, 220, 2000 millivolts, 2 volts, and 0.2 volts, 200 millivolts. When you turn the selector switch through those different ranges, what you're doing internally is connecting, here's the volts and resistance, volts and ohms socket. What you're doing is connecting that input in line with a series of other resistors, other voltage dropping resistors. The main IC inside this digital meter can only read inputs of 0 to 0.2 volts. And yet you want the meter to be able to read 2 volts and 20 volts and 200 volts. So what essentially happens is that the voltage you apply gets dropped down in a ratio of sort of 10 to 1 or 100 to 1. So if you're measuring 15 volts, what you actually find is that there's only 150 millivolts going to the main processor. If you're measuring 190 volts, you'll find that there's 0.19 going to the main processor. So that's what these dropping resistors are here. These are series resistors that drop down in a ratio of 1 to 9 or 1 to 99, or maybe even 1 to 999. These resistors on the board itself can be seen here. So these are the dropping resistors that enable the electronics to measure high voltages, even though only a small fraction of that voltage is applied to the main processor. Obviously the main processor needs to know what the dividing factor is here, and according to that it puts the decimal point in the right place on your display. So a selector switch and a series of dropping resistors for measuring your voltage. We've got the same thing again for measuring the current, because there's a series of different ranges here for measuring current, and we've got a series of resistors here, except in this case they're in parallel with the probes rather than being in series, and they're usually referred to as shunt resistors. So if you're measuring let's say 500 milliamps, what you find is that most of that 500 milliamps flows into the meter through a shunt resistor and straight back out and carries on, and a small fraction of it is fed into the meter, again because the main processor can only read these small voltages and currents. So these are the shunt resistors, and if we flip over We can see them located here. There are 4 shown here. I think there are 5 on this diagram, but one is here for the 10 amp range. This is the main, just a bit of copper bar with a bit of solder on it, which I expect is just to calibrate it to the correct resistance. So shunt resistors on the schematic diagram on the main board itself. Now we come to the main part of the meter, the brain. On our schematic we can see here it's marked ICL 7106, and that's a dedicated IC for digital meters or for digital displays. We've also got the LCD display drawn beside it here, and you can see that pins 2 right through to 20 and pins 21 to 25, this arrow here is a wee bit hard to make out. So pins 2 right through to 25 all go directly from the main IC to the LCD display itself. You know the LCD display is here in the front, and the main IC is this little blob in the back. You might be accustomed to thinking of an IC as being a sort of rectangular thing with legs down each side, but they're actually made in a lot of different packages, and this is a lot cheaper. It's actually just really built into the circuit board itself, but you can see the connections along all 4 sides of it there. So this is an ICL 7106, and it's important for your assignment that you go and find the data sheet for that and find out something about it. You'll get a bit of blurb at the start of the data sheet where it's telling you the main features of that IC. So make sure to check that out. Basically the IC can only measure 0 to 200 millivolts, or more accurately 199.9 millivolts, and that's what it puts out onto the display, except it puts a dot in the right place in order to display 1.999 or 19.99 or 199.9. So it just moves the dot back and forward depending on where you have your selector switch. So although you're measuring voltages and currents that are quite large in the real world, the IC itself here only ever really gets a voltage between 0 and 200 millivolts. Even when you're measuring a current here, it's a voltage that is then sampled by the IC itself. So you'll find out some information about that on the data sheet. Other stuff that can be seen on the data sheet then, we can see the main switch here, SW1. That's built into the selector switch in the front, so you can see it's just represented by the same sort of little pads. We've got the battery clip, 9-volt battery. We've got a low battery circuit here. This samples the battery voltage, and when the voltage gets to a certain level, it'll display something like BAT on the LCD display. You know then not to trust the readout on the LCD display. I've seen many times a meter reading a strange reading on account of the battery being low with this up, so as soon as you get this up you should change the battery. So this is the circuitry that detects the low battery. Beside it we've got what looks like a selector switch, but it's actually a set of sockets marked PNP and NPN, and they are a transistor tester, which you can see on the front here. So if we pop that back in there, you'll see NPN, PNP, and into here you can plug either type of transistor and get a measurement of its gain, which is useful if you're building an amplifier. But it's probably even more useful simply to test that the transistor is working. If you get a gain reading somewhere between 50 and 150, you know the transistor is good and hasn't been blown. So transistor tester, schematic, main meter. And lastly here you got a little bit of circuitry, which is an oscillator, along with this here, which is a little piezo transducer, and that is the sounder for the bell test on the digital meter. So if you switch around to there and you touch the leads together, you get a tone from the meter, a bleep from the meter, and that's useful for ringing out circuits to prove continuity. The last thing I want to show you is a little potentiometer from which you can do a little bit of calibration. Here's the potentiometer here, and on our schematic it's marked here, and associated with this amplifier, it amplifies the signal coming in from the sockets, whether you're measuring voltage, resistance or current. and allows you to do a little bit of gain on it before it reaches the main IC itself. So that would enable you to do a little bit of calibration on the meter if it's slightly out. So that's your lot for looking at the inside of that digital meter. This, remember, this is the main part, the main brain, so this is the bit about which you're likely to write the most. You've got to find your data sheet for that, and there'll be a bit of blurb at the front of the data sheet. So have fun with that task, folks.